In this video, we're going to be looking at topic 15b, the carbonyl compounds, and this is part of the IA2 chemistry course from Edexcel. So we're going to be focusing on aldehydes and ketones, so looking at how we name them and how we draw them, why they have specific physical properties, focusing on their solubility and their melting and boiling points, and then looking at their specific reactions, so how they react with oxidizing agents, how they react with reducing agents, with hydrogen cyanide in the presence of KCN and looking at the mechanism for that, as well as 2,4-DMPH and the iodoform test. So these carbonyl compounds all contain this carbonyl group. And when we're referring to carbonyls, we're talking specifically about aldehydes and ketones. And they contain this carbon-oxygen double bond group. And for some substances, this is part of a functional group, and we'll look at carboxylic acids in topic 15c that contains this, as well as esters. But we're wanting to focus on those that just contain the carbonyl group, and that is aldehydes and aldehydes and ketones, and those are our carbonyls. So if we start off with aldehydes, this is when the carbonyl group is attached at the end of the carbon chain, and therefore it is attached to a hydrogen. These use the suffix AL at the end, and they have the general formula of RCHO. In other words, we have an R group, the carbon, bonded to the oxygen, and a hydrogen. So the carbonyl is always at the end of the chain, and the R group can of course be any combination of carbons and hydrogens, and there's some examples in the diagram in the table. We are not interested really in the common names. The common names are there to help you because you may have heard of some of these before, specifically formaldehyde, but we want to focus on their proper IUPAC names. So methanol, ethanol, propanol, and so on. We must be able to draw the displayed formula for these as well as the skeletal formula. And of course, we should be showing all of the bonds as well as all of the hydrogens if it's displayed formula. If it's skeletal, just be aware of how we draw the carbonyl group. You can see here, so we should have the carbon being the point and the double bond coming from that carbon to the oxygen. And you have to show that it is an oxygen, and you should show the end hydrogen as well. If you leave it just like that, and you don't write the hydrogen, it is assumed that this is a CH3 group, and that's no longer an aldehyde. So you must make sure to show the hydrogen at the end. The second carbonyl that we're going to look at is a ketone. And a ketone is when we have this carbonyl group, this time in the centre of the carbon chain, and it's attached to different hydrocarbon or different R groups. So these have the suffix ONE, and they have the general formula RCOR', meaning I can have two R groups attached to the carbonyl, but they don't have to be the same. So we can call one R and the other R' just to show that they could be two different things. Now the first member here is propanone, because of course we cannot have the centre carbon of something that only has 1 and 2 in its chain. So we start here with 3 carbons in the centre, and the most basic one is propanone. Again, there are common names that you may have heard of, particularly acetone, but we want to focus on the proper IUPAC names. And as with the aldehydes, you must be able to show their displayed and their skeletal formula. This time you don't need to draw, of course, the hydrogen at the end because our carbonyl group is in the centre. So we just draw this as normal for skeletal formula, making sure that we show the carbonyl double bond to the oxygen. Now, similar to our carbon-carbon bonds that we looked at all the way back in topic 5, carbon-oxygen double bonds are made up of sigma bonds and pi bonds. Remember, sigma bonds being our end-to-end, whereas our pi bond is our side-to-side overlap. So here we get one area of electrons, whereas here we get 2. The biggest difference between the carbon-carbon bond that we saw in an alkene and the carbonyl, so if we've got the carbon-carbon and the carbonyl on the right, is that the oxygen here is much more electronegative. Of course, for a carbon-carbon, they're the same electronegativity, so your electrons are nice evenly shared. With a carbonyl group, this is a polar bond. Our oxygen is much more electronegative, so it pulls the electron density towards it, and that skews our diagram. So you can see here that they are not evenly shared. So these bubbles are your electron density, and you can see that they are much closer to the oxygen. Therefore, the oxygen has the delta negative end, whereas the carbon has the delta positive end. If we now look at some of the physical properties, both aldehydes and ketones have very distinct smells. And if you've smelled something like nail polish remover, which I'm sure some of you have, you will be able to smell the acetone from that. And it's a very specific smell, and that's kind of like a solvent smell. Our short-chain aldehydes have quite unpleasant smells. So something like butanol smells like rancid butter, which isn't particularly nice. However, as they get to be more longer chain, they become more pleasant. So nonenal, which has got 9 carbons, smells like roses. So they are very distinct in the way that they smell, and that is a physical property. Of course, you are not expected to be able to name what they smell like. This is just more for your information. When we're looking at the boiling temperatures, these are, of course, simple molecular substances. So their boiling points and their melting points are going to be controlled by intermolecular forces. And because, of course, they have electrons, both aldehydes and ketones have London forces. However, they also have permanent dipole forces. Okay, and this is mostly because we have this polar bond in the carbonyl, and that gives us these permanent dipole. Now, because of that, we see that the melting and boiling points for ketones and aldehydes are slightly elevated in comparison to alkanes. They are, however, less than alcohols because the alcohols have hydrogen bonding due to this OH group. We don't have any hydrogens in a carbonyl compound that's connected to a very electronegative element such as oxygen. So the carbonyls will not make hydrogen bonds with each other. Therefore, they do not have as high melting and boiling points as alcohols, but due to this permanent dipole, they are higher than alkanes. And as we've seen with all of these homologous series, as your molar mass increases, your boiling temperature increases, and this is due to the increased London forces because you have more electrons, therefore more induced dipoles, and then more instantaneous and more induced dipoles. The last physical property that you need to know about aldehydes and ketones are their solubility. Now, short-chain aldehydes and ketones are soluble in water, and this is because they can form hydrogen bonds with the water molecules. So whilst they cannot make hydrogen bonds with themselves, they can with water molecules. So if we take a very simple aldehyde, like ethanol, and we've got our lone pair on the oxygen, this can form hydrogen bonds with a water molecule because this is going to be slightly delta negative and slightly delta positive on the hydrogen of the water. So we can form hydrogen bonds with the water molecules, allowing them to be soluble. However, as we increase the chain length, the hydrocarbon part becomes much more significant, and that overpowers the effect of the hydrogen bonding, so the solubility will decrease. The more hydrocarbon part that we have of the aldehydes and ketones, the less this hydrogen bonding with water is predominant. And once it starts to become less predominant, it becomes less soluble. If we pivot now slightly to look at the actual redox reactions of the carbonyl compounds, you've met some of these before. Back in topic 10, you looked at their oxidation reactions, and specifically when you were looking at alcohols. And what we want to focus on now is not the alcohol itself, but of course the aldehyde and the ketone. So if we start with the aldehyde, we know that they came from alcohols, and specifically primary alcohols. And because they came from primary alcohols and oxidation reactions, they can be returned using a reduction reaction. They can, however, also be further oxidized into carboxylic acids. And again, we saw that back in topic 10, where we were looking at using distillation to make the aldehyde from the primary alcohol, whereas we use reflux to make the carboxylic acid. Comparing that to ketones, ketones can also be reduced back to our secondary alcohol this time. However, they cannot be oxidized, or they cannot be easily oxidized is probably the best way to phrase it. So our aldehydes can go in either direction in terms of oxidation or reduction, whereas our ketone can only be reduced back to the secondary alcohol that it came from. So if we focus first of all on the reduction reaction. So aldehydes and ketones can both be reduced to either the primary or the secondary alcohol that they were made from. The reducing agent that we use is this really long name here, or we can even shorten it to lithium aluminium hydride, or even easier, we write LiAlH4. Okay, this is the most common reducing agent that we use, and it has to be dissolved in dry ether. That's a condition that you must know, and it does come up in exams. So please be aware that you cannot just simply say LiAlH4, you must say in dry ether. And we can see the reduction of different aldehydes and ketones to their respective alcohols. So if we take propanol, for example, where we have CH3, CH2, CHO, because remember, of course, we have our carbonyl group at the end, it can be reduced, and similar to the oxidizing agent where we just put the O in brackets, here we put an H in brackets to show it's a reducing agent, and it requires 2 moles of the reducing agent. This will take us back to CH3, CH2, CH2OH. So this would be propanol going to propan-1-ol, the respective primary alcohol. If we were to take a ketone, for example, butanone, so we have CH3CO, CH2, CH3, again, I require 2 moles of my reducing agent, and this time I'm going to go back to my secondary alcohol. So the OH in the brackets meaning it's a branch on that carbon. So this is going from butanone, this time to butan-2-ol, of course our secondary alcohol here. And in all of these reduction reactions, the hydrogen that is added adds on to each of the atoms in the carbonyl group. So one of them adds on to the oxygen of the carbonyl group, and the other adds on to the carbon. And that's why we need 2 hydrogens in terms of our number of moles of reducing agent here. So if we look at the oxidation of aldehydes now, they can be oxidized to a carboxylic acid. And the oxidizing agent that we use will vary. And we can use acidified potassium dichromate, Fehling solution, Benedict solution, or Tollens reagent. And again, you'll have seen these back in topic 10, so you should know the different colour changes and the reactions. This time we're looking at the aldehyde to the carboxylic acid, so we only require 1 mole of our oxidizing agent. So again, if I have a very simple aldehyde, so in this case I'm going to use propanol, and I add 1 mole of the oxidizing agent, I'm going to make propanoic acid. So changing it to COOH. And you need to know the different reagents that we use as well as the colour change. So if we have acidified potassium dichromate 6, this gives us an orange to green colour, and it is because we are reducing the chromium within the molecule from +6 to +3. Now that's something that you'll look at in a little bit more detail in topic 17 when you look at transition metals. For failing solution and Benedict solution, they both have very similar reactions. We see this deep blue solution going to a red precipitate. And in both of these, it's because we have a copper 2 complex, which is blue, forming copper 1 oxide. And that is that red colour. You don't need to know the difference between these two solutions in terms of their chemical compositions, so you can use both of these interchangeably with that particular colour change. Both would be accepted in an exam. Tollens reagent is another one, which is a conversion of a silver 1 complex, which is colourless, into metallic silver, which is a silver mirror, and it's because it sticks inside the tube. So we have the metallic silver coating the inside of the tube, and it gives us this mirror look. And this is known or described as ammoniacal silver nitrate. Okay, so we're going from the colourless solution of the complex to the metallic silver. So we can then use Fehling's, Benedict's and Tollens reagent to distinguish between aldehydes and ketones. If we have an aldehyde, we will see a positive result, i.e. the red precipitate or the silver mirror. If we get no colour change, this tells us that we have a ketone. So you can see the colour changes here. So we've got this blue solution on the left-hand side, going to this deep red precipitate when we have an aldehyde. So this would be a positive result. And in the bottom picture, you can see we have this colourless Tollens reagent going to that silver mirror. And again, that's confirming the presence of an aldehyde. We can also use the triiodomethane test, or sometimes known as the iodoform test, to identify the presence of a CH3CO group. Now, this is found in ethanol, and it is also found in all methyl ketones. And when we say a methyl ketone, this means that the carbonyl group is on the second carbon. So you would have a CH3, and then your carbonyl, and then any R group. So that would be a methyl ketone, and this is tested for using the iodoform test. Now, in an exam, you cannot just simply say the iodoform test, you need to say what the reagent actually is, and this reaction consists of adding the carbonyl compound to an alkaline solution of iodine. So usually you would say iodine in the presence typically of sodium hydroxide. We then warm it and then cool it, and we form this CHI3 or triiodomethane, and this is a yellow insoluble solid, or you could say a yellow precipitate. The only problem with this particular test is it also gives us a positive result for some specific alcohols because it's actually an oxidizing reaction. So particularly secondary alcohols for propan-2-ol and butan-2-ol, both of these would be oxidized to the ketone, which would then give us a false positive. So we do need to be aware with this test that it is not the most accurate. It is a potential test, but we're probably better to use the Tollens, Fehling's or Benedict's, but you do need to be aware that this can come up in the exam. So these are just some examples of the alcohols that can give you positives and negative results. So things like ethanol has a methyl ketone in its oxidation product. Propan-2-ol and butan-2-ol will form the ketone, and again that gives you the methyl ketone giving you the positive result. So we might want to use some other tests in order to distinguish between these. Now, the one mechanism that we need to know in this particular topic is looking at the nucleophilic addition reaction of aldehydes and ketones with hydrogen cyanide. So this is carried out in aqueous alkaline solution, and it contains potassium cyanide. And this potassium cyanide acts as a catalyst. So if we say, for example, we're adding it to propanol, so we have CH3, CH2, CHO, we're adding the HCN, the hydrogen cyanide, and we're going to form a compound of CH3, CH2, CHOH, CN. So you can see here that we have this nitrile functional group as well as the hydroxyl functional group. If we were to add it to butanone, which would obviously be a ketone, we would have CH3CO, CH2CH3, again adding to the HCN, and this time our CN is a group here, and we also get the hydroxyl group on that same carbon with CH2CH3. So this is an addition reaction involving the hydrogen atom being attached to the oxygen of the carbonyl group, and the cyanide group attaches to the carbon of the carbonyl. So again, we're adding on to both atoms in the carbonyl group. Now this product is one that's a little bit unusual because we do have two functional groups here. We have a hydroxyl functional group and we have the nitrile functional group, and we call these hydroxynitriles. And when we follow the IUPAC names, we have the OH as a prefix, so we say hydroxy at the start, whereas the CN nitrile is used as the suffix. Okay, so for example, the first one that we saw would give us 2-hydroxybutane nitrile. Notice that we have extended the carbon chain here. By adding on that nitrile, it extends the carbon chain, and this is something that we will look at in a little bit more detail when we do organic synthesis, because this is a way to get an extension of the carbon chain. Or for the second one, where we added the CN and the OH onto the same carbon, we would get 2-hydroxy, 2-methyl butane nitrile. Now these are quite tough in order to name. The naming part of it doesn't tend to come up that often in exams, if rarely, to be honest. However, it is still important that you do see where those are coming from. So the hydroxy is the prefix, the start of the word, and you should say what carbon it's attached to. So in this case, it's on carbon number 2. The butane tells us how many carbons are in the longest chain, and the nitrile tells us that we have that CN group. Now, in terms of the mechanism that we have to know, it is a two-step mechanism. The first is the nucleophilic attack by a cyanide ion, and then we get a reaction from the intermediate. So if we just take a very basic carbonyl compound, so we have the CO, and in this case with a hydrogen, and I'm going to have it as ethanol. The ethanol is attacked by the lone pair that is present on the CN. So this comes from the K plus CN minus. So the potassium cyanide that is in here in this mixture is acting as a catalyst here, and it's giving the cyanide ion. That is then going to attack in at the carbon here, because this carbon is very delta positive. It's quite electron deficient because the oxygen is much more electronegative. We will then get a curly arrow going from the double bond onto the oxygen, and that makes an intermediate. So we have the carbon with its hydrogen and its CH3 attached. That has not changed. Now, however, we have added the CN. So we now have a bond between the carbon that was present and the new cyanide group that has been added. And the oxygen that was present has now become negatively charged with that lone pair. That lone pair can now react with the HCN that is present, and it will attach onto the hydrogen, and you get again a curly arrow onto the CN, and I'm going to draw it down here just for space, so that we've got the carbon in the centre with the hydrogen and the methyl. None of that has changed. We added on our nitrile group, and now we have a hydroxide, and we have reformed the cyanide ion. So this is showing why the cyanide acts as a catalyst, when it's in the potassium cyanide because we're reforming it at the end here. So you need to know this two-step mechanism, the nucleophilic attack at the first stage, and then the reaction between the intermediate and the HCN to make your hydroxynitrile with your cyanide ion being remade. Now we can use optical activity as evidence for this particular mechanism. When we have a look at the carbonyl group, what we can see is it is actually a planar shape. So we have our hydrogen and our methyl group attached, and the CO is planar. So you're going to get this delta positive carbon and delta negative oxygen. Because it is planar, that means that there is equal chance of attack by the cyanide ion for either the top or the bottom. So we can have the cyanide attacking in here, or we could have the cyanide attacking in there. And if that happens, we will make two different enantiomers because our product formed would have a chiral center. So we could have this enantiomer where we have the CH3, the OH, and the H, or we could have the other enantiomer. That should be a wedge bond, where we have the wedge bond and the hash bond, like that. And you can see that these are non-superimposable mirror images of each other. And because there is equal chance of attack, that means that we're going to form equal amounts of each of the enantiomers. Therefore, we form a racemic mixture. So because our product mixture has no optical activity, it is confirming that we have a racemic mixture because there is equal chance of attack. And that is all to do with the planar carbonyl. We saw a similar sort of explanation in topic 15A when we were comparing the SN1 and SN2 reactions. It's the same thing here as it was with the planar carbocation. This time we're just focusing on the planar carbonyl group. Now the last nucleophilic addition reaction we have to look at is with 2,4-DNPH or 2,4-dinitrophenylhydrazine. We can also call this Brady's reagent. Each of those three names would be accepted in an exam. And these will react with carbonyl compounds to form an orange precipitate. And you can see that in the diagram here. And this is a positive test for the presence of a carbonyl compound. And we have the reaction at the bottom here. You are not expected to be able to draw this reaction. This is just for your information. What you are expected to do is to be able to name Brady's reagent, give the positive test, and explain what it's testing for. So you could test a particular organic substance to see does it have a carbonyl using Brady's reagent, and you would then further test it using perhaps Tollens, Benedict's, or Fehling's solution to see is it an aldehyde or is it a ketone. So this would be your first test and your steps just to confirm yes it is a carbonyl or no it is not. The other very useful thing about 2,4-DNPH is we can actually analyze the derivatives of these compounds and we can identify the individual carbonyls. The reason that we have to do this is some of the carbonyl compounds, when we're analysing them, we may be using melting point analysis. But a lot of similar carbonyls have similar melting points, so we can't necessarily tell them apart. For example, pentan-2-one and pentan-3-one have the same boiling temperature, but of course they're different isomers of each other. So what we can do is we can react it with 2,4-DNPH to make these derivatives. Now, a derivative is a compound that is formed from a similar compound by a chemical reaction and it maintains most of the same structure. Okay, so it's sort of the parent compound would be the carbonyl and the derivative would be like the kind of offspring compound, if you want to think of it that way. The derivative can then be filtered, purified, dried, as we would do with any other organic substance, and we can determine their melting point. So if we were to take, for example, the derivative of butanol, that would be 2,4-dinitrophenylhydrazone. So we have this ONE ending. Again, you're not asked to name these. It is just simply to be aware that we can use these derivatives. So if we look at one in more detail, if you compare pentanal, pentan-2-one, and pentan-3-one, they're all very similar and they all have the same boiling temperature. So without the use of something like IR or with NMR or any other spectroscopic method, we can't tell these apart. What we can do though is when we react them with 2,4-DMPH, we can make our derivative, and you can see that we have a big difference in our melting temperatures. We go to 104, 144, and 156. So now we can tell them apart. Now let's finish off by looking at some past paper questions, as we do with each video, and we're going to be looking at some multiple choice as well as some written questions. So first of all, we want to be looking at the reactions for ethanol and propanone and looking at Tollens and the 2,4-DNPH. So we know that Tollens reagent is a positive test for an aldehyde, and it is only for an aldehyde. So for the ethanol, this is going to be the aldehyde, whereas the propanone is a ketone. Now both of these are carbonyls, so of course both of them will react. So then with the 2,4-DNPH, so we can get rid of B and C. So that leaves us with A and D, and because the Tollens is only positive for an aldehyde, only the ethanol can react, so our answer must be D, because propanone will not react with Tollens reagent. We want to now compare ethanol to propane in terms of its boiling temperature and its solubility, and the difference in these properties is best explained by the fact that in addition to London forces, ethanol can also do what? So ethanol cannot make hydrogen bonds. We've said that it doesn't have a hydrogen connected to a very electronegative atom, so it can't be A. We know that we've got permanent dipole-dipole forces being present, and we can also make hydrogen bonds in an aqueous solution because we're making hydrogen bonds with water. So our answer is actually B, but let's just double check the others. Again, we can't make hydrogen bonds in the liquid state because the ethanol can't make hydrogen bonds with itself. And the permanent dipole-dipole forces for D are present in the liquid state, but that does not tell you why it's soluble in water. That can only be explained using hydrogen bonds the ethanol makes with water. So our answer here has to be B. For question 3, we've got some chemical tests. So number 1, warm with Fehling's or Benedict solution. The second test, warming with iodine and dissolved in alkali, so your iodoform test. C, adding sodium carbonate solution, and D, adding 2,4-DNPH solution. So we want to see, first of all, which test would result in effervescence with the compound given here, and we can see that we have got a carboxylic acid or a carboxyl group here, and we'll talk more about that in topic 15C. But because it's got this carboxyl group, it is going to react with something that is a base. So our answer is going to be C, the sodium carbonate, because we'll be making carbon dioxide. The test to distinguish between aldehydes and ketones, well, that's our first one, which is our Fehling's or Benedict solution. We would see that blue to the red precipitate. Which one gives us an orange-yellow precipitate with propanone, this carbonyl compound, and that's our 2,4-DNPH. So now we want to look at some written questions. So this is some reactions involving ethanol, which is CH3CHO. And ethanol is a carbonyl compound. We want to describe the test. So we've went over this just a couple of times now. So we want to say we are going to add Brady's reagent or 2,4-DNPH. That is, of course, also acceptable. And then with any sort of description of any chemical test, we must say the reagent as well as what the result is. And our result is that we form an orange precipitate. And you must use the term precipitate. They will not allow you any mark for the second part if you just say you see an orange colour. You have to be very specific that it is a solid or a precipitate. And then for part B, we want to identify by name or formula the reagent to carry out reaction A. Well, that's going from the ethanol to the alcohol. So we know that this is a reduction reaction. Therefore, we need a reducing agent. So our answer is always LiAlH4. It does not say about the particular conditions that we need, but we should always state that it requires dry ether because it's just good practice for us to do that. For part C, we want to identify 2 organic products that come from this one. So this is our iodoform test. So the first one that we always make is going to be the triiodomethane, or CHI3. Okay, it doesn't say specify by name. It could be the formula as well. And because one of those carbons is going to come off of the chain and react with the iodine, that leaves us with 1 carbon. And the other thing that we make here is going to be our sodium methanoate. So the CH3 is going to react with the NaOH, and we would make HCOONA. That would be our second organic product. And what would we see is a yellow precipitate, because remember that triiodomethane is a precipitate and it is that yellow colour. So now we want to name the type and mechanism that occurs in reaction C. So this is the HCN and KCN. Well, this is going to be our nucleophilic addition reaction. So we have to make sure that we have both nucleophilic and addition. And we want to draw the mechanism for this as well. So we want to have our ethanol and how it reacts with the HCN and KCN, including all curly arrows, dipoles, and lone pairs. So we're going to have our carbonyl group like that. And we, of course, have our CH3 and our H. We've got the CN and our lone pair. Sorry, CN, not CH. And our lone pair is going to attack in at the carbon because the carbon is delta positive and the oxygen is delta negative. And that is going to then go to the oxygen like that, giving you the intermediate where you have your CH3 and your H as normal, but now you have attached the CN group and you have your O minus. That's then going to react with the HCN, which is delta positive. And of course, we draw our lone pair like that, going onto the carbon. And then again, I'm going to draw it down slightly here. You try and keep it in a straight line, of course. And we've got our CN with our CH3, our H and our OH, and showing that we have reformed our CN. So you would get 1 mark for showing your dipole and your lone pair on the carbon of the CN, so it has to be on the carbon. Then you get a 2nd mark for your lone pair, curly arrow to the carbon, and then the 2nd lone pair to the oxygen. Getting the correct intermediate would be the 3rd mark, and then the 4th mark would be the curly arrow from the lone pair to the hydrogen, as well as the structure of the product. And the organic product of this reaction is a racemic mixture. So first of all, we want to state what is a racemic mixture. So this is a mixture of equal amounts. So it's very important, you have to say equal amounts of 2 enantiomers, or 2 optical isomers. Or you can say D or L isomers, they are equimolar, they have a 50-50, something that references equal amounts and that you have 2 enantiomers. And now actually referring to the reaction, why does this racemic mixture form? Well, our aldehyde has a planar carbonyl group. Okay, so we have to be specific. Talking about the carbonyl group, we cannot say ethanol is a planar molecule because it's not. The ethanol does have a shape to it. However, the carbonyl, the CO bond, is the planar part. And because it's planar, the CN can attack equally from either side. And you could say from right or left, top or bottom, above or below, however you want to phrase it. But the most important part, the carbonyl is planar, therefore the nucleophile can attack equally from top or bottom, and that gives you your racemic mixture because you can form both of your enantiomers. So there's the mark scheme for the first couple of questions, and again you can see how the marks are breaking down for your Brady's reagent and the colour change, making sure that you say both of them. And in particular, I would pay close attention to the marks on the mechanism so that you can see exactly where the marks are breaking down for that. But that's everything for topic 15B, carbonyl compounds. If you do have any questions, please do feel free to leave a comment below and I'll get back to you as quick as I can, and we hope to see you back soon.